software and developers, ladies and gentlemen. Let's proceed with our sessions. We have one more very, very, very exciting talk that Stephen is gonna crush right now, and he's ready. As you can see him right here, he's gonna talk about Pocket Polyglot Mzansi, and yeah, it's a machine learning talk. Seems like this is a machine learning room anyway, but let's give him a lot of applause so that he can start his session with brevity.
Good afternoon to the few brave machine learning folks around. There's been a few talks on language models and agents. So I think in this talk, we're just going to take one step back and just talk a little bit about developing language models. Specifically, in this case, talking about machine translation and talking about South African languages, but that applies to what we would call lower resource languages more generally. So Google Translate already exists. Why bother with this research? Slightly facetious question, I asked it myself, but there are many reasons. The first, I think the big one, is that most leading machine translation systems are proprietary. And there are many good reasons that I don't think we have to enumerate in this room to pursue open science and open source software. Commercial systems are cloud-based, and there is often a need to be able to do these things like offline, on limited memory, on edge devices. Commercial systems do not focus on low resource languages. In cases they may support them, but there's no focus to curate good data sets, to train the models. And then importantly, because it's fun. It's a fun challenge, it's fun to train models, and working with small models is a very good way to learn about machine learning and NLP. Very briefly about me, I'm a hopefully improving Python coder, machine learning researcher. I'm a healthcare actuary, although some might say lapsed. And I'm very interested in small, focused machine learning models that solve real problems. I'm currently going through, I suppose, a bit of a career break or career reevaluation or whatever you want to call it. But that being said, I recently joined on a part-time contract basis an amazing value-based healthcare organization called Aligned. So if you're at all interested in the healthcare space, go check them out. Okay, so a brief overview of neural machine translation. Can I do a talk about that without having the graph from the Transformers paper in your presentation? So there you go. They're encoder-decoder designs. I'm not going to go into too much detail here, so happy when we do the Q&A to expand on these things. But basically, most of the LLMs today, the generative LLMs, are decoder-only models. The encoder has a first step where we take the input text, encodes it, and a separate decoder then decodes that, generates, from those latent representation of the input created by the encoder, takes that and generates text in the target language. Each input, when we have the input text, we break them up into tokens. Convenient to think of tokens as words, although in practice they're smaller units than words. They get embedded, basically, converted into vectors, and then the self-attention is the mechanism through which relationships between tokens are then learned. Training data for machine learning systems, they primarily trained on what's called bitext databases, bilingual corpora. So that's basically, you have text in one language, and you also have text in the second language, and you feed that into the model to try and learn those relationships from the one to the other. There are different types of bitext available. As you can imagine, it's very, very scarce relative to just monolingual data that exists on the internet. So there are three main types of bitext data that we talk about. The highest quality is human translated text. That is the scarcest by a long way, and virtually non-existent for lower resource languages. Then we have mined bit text data, so that's basically using heuristic algorithms to try and align texts that are available in multiple languages and break them up into paragraph sentences or whatever units. So that's relatively abundant compared to human translated text, but it's also relatively noisy. And then a third form is back translated data, where you use an existing translation system to create by-text data from that. There are some methods to use monolingual data to train translation models. They're usually used as a bit of a pre-training step, so you then still need a lot of by-text data to fine-tune the models to become really good at translation. I just want to make a quick note about this No Language Left Behind project in LLB, because I'm going to reference it quite a few times in this talk as a benchmark. It's a project from a few years back from Meta AI, truly open source, not just weights, training code, all the code to reproduce all the training data. They released it with a 192-page paper. Lots of experiments. Kind of shocking when you read it now. Sort of when we've gotten used to sort of model release by short blog post. They translate over 200 languages, including 55 languages that they say are quote spoken on the African continent. 9 of South Africa's 11 written languages are included. And then they released 4 model sizes, the smallest being a 600 million parameter model that I'll use a bit in this talk. So then just quickly to state the research objectives, what we try to explore is basically asking the question, can we train either from scratch or through distillation a translation model that is capable of running offline on a device such as a smartphone, has no more than 50 million parameters, able to translate 6 South African languages as a starting point, and then achieves accuracy that is comparable to the 600 million parameter in LLB model, which is of course more than 10 times bigger. Why 6 languages? Honestly, it's a little arbitrary. It's a start, also a choice of convenience. I initially did 4 in the first version of this model, and then expanded to 6. I think the thinking is sort of just intuitively that it's reasonable to expect that there's some relationship between the model capacity, the model size, the number of parameters, and the number of languages that it can translate. And I'm sort of thinking that if you just think of the number of layers or the number of parameters in a model, that some of them are very language specific, probably in the first or last layers in like encoding and decoding, but that there'd be a lot of sort of language agnostic sort of knowledge, I guess, stored in some layers in more of an embedded, latent kind of space. So that, I think, relationship needs a little bit more understanding, but that's sort of the thinking. So the included languages are really picked from the census, the top 6 South African home languages, but also a little bit of thinking in that try to be careful to include the 3 major different language groups in South Africa, the 2 Germanic languages, Nguni languages, and then languages from the Sotho-Tswana family. I'm going to very quickly go over recent work. Maybe just suffice to say that there's been some amazing work, and a lot of it from African-led research groups on machine translation and NLP more generally that include African languages. The 7th Conference on Machine Translation, WMT 22, which I also referenced a few times, included a track that just focused on African languages. But where this work is different is that it focuses on much smaller models. I think there's been a bit of a shift in what is considered small. Looking at the submissions for the WMT 22 conference, I think the smallest model was a submission from UCT, and I had what is it? Yeah, like almost 300 million parameter model, which is considered very small today, which, a few years ago was considered, for those of you know sort of the history of LLMs, the biggest BERT model was, I think, 340 million parameters, and that was considered gigantic 6 or 7 years ago. Right, so model architecture. So if we have a model that has 600 million parameters, and you have a goal to make it smaller, you want to get it to I said 50 million parameters, it's quite useful to understand where the parameters are used. I think people talk about a weights or a parameter budget at times. So we can break this up into 3 main components. There's an embedding layer, so that's basically the relationship between the tokens, the subwords, sort of connecting them with vectors or representing them in vector space. And that is directly proportional to the size of the vocabulary. So how many tokens you have in the vocabulary. So in the NLLB project models, they use a vocabulary size of 256,000. And then each of those tokens are represented in the 600 million parameter model by 1,024 dimensional vector. So the number of parameters as you multiply those together, and that gives you 260 odd million parameters. So just embedding the tokens, you're already up to 260 million parameters. So clearly, if you want to get down to 50, you have to do something probably about the vocabulary size, probably about the dimensionality. So that's number one. And then the encoder and decoders each consist of 12 layers, and each layer are about 12 odd million parameters in the encoder, a little bit more in the decoder. So they contribute 150 million and 200 million parameters respectively. So then looking at our model, how did we get to 50 million? The first is to dramatically reduce the vocabulary size to 10,000 tokens. There is a belief that you need, if you want to do multilingual translation, you need really large vocabularies to be able to represent more of your text as like words. The smaller the vocabulary, the more sort of tokens you typically have in your input. You have more words that you break up into smaller little pieces, so you have longer inputs, and longer inputs are harder and more expensive to model, so there's definitely a trade-off, but I haven't found too many good like experimental like papers on this relationship between vocabulary and performance. Reduce the number of layers from 12 to 6, reduce the dimension size, like half those, half the dimension of the feed-forward network inner layer, and that gets you down to 49 million, so just under 50. So to maybe just illustrate that slightly differently, if you start at 615 million, just by reducing the vocabulary, you go down to 360 million parameters immediately. A little bit of another 100 million when you reduce the dimensionality. Another 170 million or so that you lose when you reduce the hidden layer size and the number of layers, until you get down to 50 million parameters. Experimental setup, I'm not going to say much about specific evaluation metrics, perhaps just a few general remarks. Metrics is an important area, and I think we often speak in metrics in very objective terms, like this model is better than this model because of some sort of leaderboard score. I think it's important to understand that all metrics have limitations and they convey different bits of information, and that we should always consider multiple metrics, but there is also the element of convenience that to be able to compare, we tend to report things that others have reported too. I'm really struggling with time, so I'm going to skip over the basic training procedure, but maybe just to say at the bottom there that all experiments, all the models that I trained can be trained on consumer hardware, consumer GPUs. Everything can run on a NVIDIA A5000 GPU with, I think, 24 gigs of RAM. All the models trained for the biggest model that I have trained for about 20 hours on an A5000. And if you rent those from Jarvis Labs for 44 US cents an hour, it costs under 200 Rand. Training data, I mentioned the WMT22 data set. I'm not going to say much more about that, but those are the language pairs of the languages that I'm interested in that are in that data set. Maybe just before I go, this is in the category of the mined bit text data, and it's really noisy. If you read through them, some of the translations are, like obviously wrong, and frankly, some are funny. So then back translations, also created a set of back translated data where I took all the English sentences in a subset of WMT22 and used the small NLLB model to create translations. So that is one of my data sources. And then the evaluation is on a data set, a benchmark called Flores 200, which consists of 1,012 hand-translated, expert-translated sentences. So it's a very high-quality evaluation data. Primary results, the answer to the question is, I think it's a resounding yes. It is possible to train a model with fewer than 50 million parameters that remain competitive with NLLB, the 600 million parameter model. This model is, in terms of parameters, 90% smaller than NLLB, the 600 million parameter model, but sacrifices only about 5% in accuracy in terms of the char-F++ metric. I'm just going to run through a few sort of secondary results very quickly. I've got 3 slides on each of the 30 language pairs that you construct from having 6 languages. But maybe something that, if you have some time to look at that stands out is that our model underperforms on English. Multilingual models typically are strongest when translating into English, so from any language to English, because in the data sets there's usually a relative abundance of English, so it gets very strong at that. I used back translated data mostly, which created a very balanced data set, so there's no gap in English, in the English translation as a target, which is obviously an area that one could optimize for by just adding, more English. Some other findings found that the back translated data worked much better than just training on the raw data. I think this is more of finding about data quality than anything else. So I think a big point is better data sets. A lot of experiments on teacher-student distillation that didn't really work here. Another finding that's been confirmed by others is just once you've trained a model, fine-tuning on just a small amount of high-quality data can really make a big difference. Increasing the model's vocabulary without doing anything else. To one of my earlier points, perhaps unexpected but made no difference. There are good reasons for it, but I think they're worth exploring more. Played around with different configurations of the encoder and the decoder. No evidence to suggest that they're just going with, sort of 6 and 6, the same number of layers, are suboptimal. Did some experiments on different initialization strategies that I also just go over very quickly or skip over. And then finally, so now we've really shrunk the model. What if we make it a little bit bigger? So if you increase the number of encoder and decoder layers from 6 to 9, increase the dimension of the latent vectors a little bit, basically doubling the size, or more than doubling the size of the model, it only results in a modest boost of accuracy, suggesting to me that the real breakthroughs are elsewhere, probably in the data, but also sort of architectural. And that then gets me to my final thoughts, which is first to say that bigger models are not automatically better, for specific tasks. I think we should resist the scale above everything else hype that we're currently seeing. High quality data for African languages is very much needed. And then just perhaps more sort of philosophically, just training machine translation models on these parallel corpora just seems a little inefficient, that we need to explore new approaches to use what's called self-supervised learning more effectively. And that is it. some resources, if you're interested, model weights. There's a little online demo. The data set that I created is available on Kaggle, and the training code is coming soon when I've made it slightly less embarrassing.
Thank you, Stefan, for such an amazing and wonderful research you have done. That is very, very, very worthy. And I think everybody in the room, if at least you might not bump into him again, you may take a picture of that. I think he also needed to share his slides so that any researcher that is interested in, the same topic can further, go and explore. So I will accept at least 2 questions from the audience because of time, because we have to break for tea break.
I'm Shani, good afternoon. As a polyglot myself, I'm very excited about this. So I just wanted to find out, like currently I'm working on translating certain data sets, but what the current tools does not give us is the authenticity of the meaning of those words. I'll take a saying for an example. So if you put a saying in ChatGPT or in Google, whatever translation, it will give you the direct translation. However, what we are looking for is maybe an English version of that saying, not really the translation of that what it's saying. So are you taking things like that into consideration in your polyglot tool? Thanks, that's my question.
Yeah, so I think that's sort of the point that I made when I said earlier that the commercial systems might support local languages, but there's no focus on them to understand nuances. So the answer to the question is it's data. We need data sets that contain those nuances if we want to encode them then in models. And also why doing sort of open research is important, so that we can take these models and fine-tune them on data sets like that to produce the outputs that we want to see.
I just wanted to ask, the part in the slides where you speak about reducing the dimensionality of the model, to do that, did you use mathematical operations on it like PCA or SVD? Just how, basically?
Yeah, good question. So no dimensionality reduction techniques like that. The models were trained from scratch. So it's basically initializing them with smaller matrices, random parameters, and just running backpropagation, machine learning training on that. I did play around. That's one of the slides, when I started to run out of time that I skipped over. I tried to play with some of those kind of pruning techniques, but let's say I start with a pre-trained model and it has, like vectors of 1,024 dimensionality. You go can we halve them by averaging them up or dropping alternates? And I think that works really well up to a point. I think the scale of the pruning here is too much. If you sort of reduce it by 10 or 20%, that's extremely effective, but not at this scale of pruning.
Can take one more question before we break for tea break. Oh, I have a question. When is the training code coming?
Oh boy. I mean, maybe I should. This is a good opportunity to put pressure on myself. It's sort of ready. It's just it's experimental code. The intention is not to make it production ready, but like I said, it just has to be a little less. Sort of need to remove all my comments to myself, like "Don't do this, you dummy." But soon, in the next few weeks, hopefully. Yeah.
Thank you, Stephen. Can you please give me a round of applause? And then, ladies and gentlemen.